Hello everyone, thank you for joining us in our introductory video of the Yamashita-Set laboratory. We are located at the Research Center for Advanced Science and Technology in the Komaba Research Campus for the University of Tokyo. We are a lab that focuses mainly on laser technology, be it ultra-fast lasers or fiber optics, fiber lasers, and measurement technology with lasers. So without further ado, let's get into what our laboratory has been up to. But before we do this, let's generally introduce the concept of light and lasers and fiber lasers so that we can all understand better what the lab is doing these days. The first concept we'd like to introduce is the idea of a laser and the idea of light. So when we think of everyday light and we think of a laser, what are the differences? How do they differ? Are they the same? The answer to that is no. Light from a light bulb, which can be considered everyday light, is unsynchronized, has many colors, and it goes out in all directions. Whereas light from a laser, known as coherent light, has the same color, the same direction, and it's synchronized, as you can see in this figure on the right. The laser itself was invented by Theodore Maiman in 1960, which shown on the right here is the ruby laser. And the laser itself opened the door to many different optical applications, many of which are being explored in our laboratory these days. One such innovation was in 1964, the Nobel Prize in Physics was awarded to Townes, Bazov, and Prokhorov for their work on the microwave laser. Now, when we think of everyday uses of lasers in our daily lives, what do we think of? Of course, there's the common laser printers and laser pointers, but if we think even a little deeper, we'll realize even in CD, DVD, Blu-ray players, we use lasers. In our optical mouses, we use lasers. And then if we think even further, we'll realize that the internet is pretty much based off fiber optics and lasers, in the sense that all this information in the internet is being carried over long distances, be it from America to Europe, all in fiber optics with light. So currently, fiber optics and lasers play a huge role in our internet. Now, one important concept when we're talking about lasers is the notion of a continuous laser, where the laser's power is constant over time, it doesn't change, versus a pulse laser, which emits small little pulses every now and then. And so, as opposed to the continuous laser, which can be seen as a hard-working laser, which is always outputting power, the pulse laser is kind of a lazy laser in the sense that it outputs a pulse, and then for 99% of the time, it doesn't output anything, and it outputs another pulse. The only difference is that a pulse laser is actually more efficient in the sense that within this small little pulse, it has a very high energy that can be sent out very long distances and can carry a lot of information, as opposed to a continuous version. So that's why our lab is interested in developing pulse lasers. And more specifically, we are interested in ultra-fast lasers. And to better understand this topic, let's look at light and how fast it travels. So light is the fastest known thing in the universe. And if we think about how far light travels in 1 second, we'll realize that it does around 8 times the circumference of the Earth. Now, if we take this 1 second and cut it into 1,000, 1 millisecond, we'll see that in the blink of an eye, light will travel from Tokyo to Sendai. And then if we cut this time into 1,000 smaller units, 1 microsecond, the shutter speed of a camera, we'll see that the light has traveled 300 meters. And if we keep breaking this light down, we'll eventually get to the width or the distance that an ultra-fast laser pulse width travels. So we're talking about picosecond, femtosecond lasers with a pulse that only travels 0.3 millimeters. If we compare that to the time for 1 second, which was 8 times the circumference of the Earth, you can see that this pulse is very, 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 very small. And to better understand pulse lasers and fiber lasers, let's take a brief look into the history of pulse lasers. So the first pulse laser was invented in 1965 with the idea of mode locking. And then in 1982, the titanium sapphire laser was invented. Now, an important discovery was, or invention was that of the first fiber laser and amplifier in 1986. Fiber optics offer a cheaper, more reliable, more robust alternative to what was previously done. And so this really opened the door to fiber optic communications and communications over very large distances. At our lab, we're proud to say that in 2003, we invented the carbon nanotube ultra-fast fiber laser. And so one of the specialties of our lab is actually ultra-fast lasers, or picosecond, femtosecond pulsed fiber lasers. In terms of optical fiber and optical communications, one of the key milestones was that of Charles Kao in 1966, who invented optical fiber. In 2009, he was awarded the Nobel Prize in Physics for his invention. Optical fiber drastically changed the optical industry because we were now able to confine light into a tiny and thin fiber and send it very long distances. And as a result, many applications arose from this, several of which we'll get into later on in the presentation. Now, why is a fiber laser with an ultra-fast pulse so much better than conventional lasers? Simply put, conventional laser has a higher cost, it's bulky, it's large in size, it has high power consumption. If you look at this on the left here, it's a huge, huge endeavor creating this laser, whereas a fiber laser can be held in your hand. It's very low cost, compact in size, and it's efficient in power because of the pulse. So with this in mind, it became very affordable to many labs, it sped up R&D, and it was a practical solution for many new applications. And with this in mind, let's talk about what the Yamashita-Set lab has been up to in the past in terms of applications of ultra-fast fiber lasers. We've split our applications today into industrial applications and biological applications. So the first of the industrial applications is LiDAR, or here we've shown you a 3D scanning example where light from a laser is emitted. It bounces off a surface which has a different shape and is reflected back into our detector. And so based on where we emit this light, if we emit it here, 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 we can get very precise reconstructions of the surface. For example, this small surface here, you can see it's comparable to a 100 yen coin. We can reconstruct it quite precisely with the hole and the circle. Even this 4-leaf clover over here, you can clearly see the definitions, the distinctions in the surface. And this jug over here as well, easily reconstructed. And this is just from bouncing the laser at many, many different points and gathering all the data together. So this is an example of 3D scanning. And here is one of the devices we have in our laboratory as a 3D scanner in which we're using to reconstruct different objects. And with this, you can get very precise information on the objects. For example, are there cracks that shouldn't be there? Is it defective? And like, for example, in this helmet, we were able to reconstruct it very precisely. Another application we've been exploring recently is the idea of wind sensing, what is known as Doppler LiDAR. Doppler LiDAR is used in a variety of industries for wind speed measurements. It's capable of measuring wind speeds very, very far away and can give us a good idea of what the wind is going to be. For example, it's used in wind turbine farms to align the wind turbines in the correct direction to optimize power, or it's used in airports to detect dangerous wind patterns that can damage the plane or even crash the plane. And it's used in meteorology to bridge the gap between what satellites can see in the upper atmosphere and what we can see in the lower atmosphere. Doppler LiDAR works similar to the LiDAR that I showed you in the first slide with 3D scanning, in the sense that the light is emitted, except this time instead of reflecting off a surface, the light is actually scattered off aerosol particles and captured by our detector. And like its name says, based on the Doppler shift, we can determine the wind speed of this group of aerosol particles. And to better understand this, let's take a zoomed in look on this particle. So if we look here, this is the particle, and we've modeled the light waves as these circles. And so we can see that if we put our detector here, or if we put our detector here, the light waves that we'll see are different. These are very spaced out light waves, whereas these are very close light waves. And so based on the movement of this aerosol particle, these light waves will be very closely spaced together or very far from each other. And we can detect this and actually determine how fast the particle is moving and how fast the wind is. And with this information, we can get very precise wind maps around our location. So if we're centered over here, we can point our laser in all these different directions and get a really precise idea of what the wind is like all around us, very, very far away, like 30 kilometers away. Now, into the biological applications. OCT, or optical coherent tomography, is a current device used in the medical field. And as opposed to Doppler LiDAR and 3D scanning and LiDAR in general, which provides us long distance information, sometimes very, very far away, OCT works in the sense that they can give us very, very precise imaging. So if we look at this plate over here, this is a Japanese character right over here, small, very small, 0.5 millimeters. We can tell the difference between these triangles. So OCT, based on the principle of interference, so we send light to our sample and we interfere it. And based on this interference, we can get these very, very precise reconstructions. Another biological application that we've been looking to is what's known as two-photon microscopy. And we've been using it for the imaging of live insect brain cells. This project is a multidisciplinary research project with collaboration in another laboratory in RCAST. It's the Kanzaki Lab, which is an expert in biological science. And so in conventional two-photon microscopy, a laser system is very expensive and bulky. So in our lab, we're trying to develop the same system using an ultra-fast fiber laser, which, as I said, is much more affordable, compact, and flexible, durable. So it can provide many advantages over the current methods. Another advantage of two-photon microscopy is you can see with a conventional microscope and a two-photon microscope, the quality is much, much, much better. And this is an image of a honeybee brain, antennal lobe, taken using a two-photon excitation fluorescence microscope that our laboratory has developed jointly together with the Kanzaki Lab in RCAST. The antennal lobe of the bee is a very important part of the insect brain, It helps insects to sense the world around them, like smelling, for example. Taking live images of the honeybee brain helps us to understand how external information is processed by the brain, which is very important to neuroscience research. Uh, ultrafast, ultrafast lasers allow us to see deeper, clearer, and sharper images of biomedical samples such as living brain cells, as I'm showing you in this picture over here on the right. Here we have a conventional system, and if we compare, for example, the 30 micrometer sample with that of a 2-photon microscope, we can see that this image is much deeper, clearer, and sharper than conventional methods. So that's an added benefit to the society at large. Another example is our research collaboration with Professor Nuria at Keio University, which is using 2-photon microscopy for advanced research of live brain cells and brain tissues, such as nerve cells and glial cells, to understand the control mechanism. 2-photon microscopy is an important tool for such kind of research activities. Another biological application explored by our laboratory is what's known as stimulated Raman scattering microscopy, which is capable of very high-speed imaging of live cells, such as cancer cells, and is a very useful tool for many biomedical research, such as cancer research, for example. The stimulated Raman microscope is also relying on an ultra-fast laser at the core of the measurement technique, and it's another collaboration with Professor Ozeki, the Department of Electrical Engineering in UTokyo. So to conclude, today we presented with you some information about our laboratory, how we're developing laser technology in terms of ultra-fast lasers, fiber lasers, fiber optics, and measurement technology that are based off of this laser technology, such as Doppler LiDAR, 3D scanning with LiDAR, OCT, stimulated Raman microscopy, 2-photon microscopy, and there are even more topics that we're exploring in the laboratory. So if ever anyone is interested in coming to visit us, please do not hesitate. We'd love to show you around. As for now, thank you for listening to our presentation, and I hope everyone has a good day.